Hello everyone. So previously we had discussed on the topic modular inverse algorithm, right? So today we'll be discussing on the topic Chinese remainder theorem, right? So extension to the modular inverse actually. Yeah. See, the Chinese remainder theorem is a number theory algorithm that provides a unique solution to the set of modular equations. Set of modular equations when the moduli are this one are pairwise coprime, right? So when the moduli are pairwise coprime only, so this one we have to keep in mind. Yep. So the Chinese remainder theorem is a number theory algorithm that provides a unique solution to the set of modular equations when the moduli are pairwise coprime. Yep. In simple terms, it helps find an integer that satisfies several modular constraints simultaneously. Several modular constraints simultaneously. Right. Let's go with the explanation part here. Let's see. Suppose we have the following system of this one congruences. They have strictly mentioned here. X equals this one A1 mod M and A2 mod M. This one mod M2 and A3 mod M3. Right. So if M1, M2, and M3 are pairwise coprime, so this one we have to keep in mind M1, M2, and M3 values. So mod, suppose for example 7, 11 as well as the 17. Suppose this is 7, so suppose this is 11 and the 17. So they are the coprime, right? So we have to consider prime numbers in the place of M1, M2, and M3. Suppose if M1, M2, and M3 are this one pairwise coprime, then there exists a unique selection modulo M where M is equivalent to the M1 into M2 into M3. Yep, is equivalent to the M1 into M2 into M3. So to find that solution, we make use of the formula this one. We'll be going with A1 into M1 plus this one A1 into M1 into Y1 this one until here. This is one thing. A1 into M1 into Y1, A2 into M2 into Y2 plus A3 into M3 into Y3 model, right? So A1 M1 then into Y1, right? A2 M2 into Y2, A3 M3 into Y3. Yep, total modulo M, right? Mod M. So where M1 is equivalent to, so this M1 is equivalent to the M divided by M1, same goes with the M2, M by M2, M3, same thing, similar thing, M by M3, right? So Y1, this one, Y actually, Y1, Y2, Y3, whatever we have considered here, A1 and M1 is fine. M1 is nothing but M by M1. We know this one, this is fine. So what is Y here? They have strictly mentioned here. See, Yi is the modular inverse of Mi modulo Mi, right? So this one, capital M and small m. Don't get confused here. Yi is the modular inverse of Mi modulo Mi, right? So this method efficiently combines what it combines multiple modular equations into the single unique solution, right? So this method efficiently combines multiple modular equations into the single unique solution, right? So now let's move on with the further things. Let's do one thing. Let's start writing the code. Let's start writing the code in the sense. Let's try to implement the exact same thing, whatever we discussed in the explanation part. Yeah. So let's start writing the algorithm. Yep. So this is fine. Let's do one thing. First, let's write the function to find the modular inverse using the extended Euclidean algorithm, right? So I'll just go with def here, mod inverse of n comma m. So this is fine. N comma sorry, a comma m we have to go with, right? A1, M1, A2, M2, A3, M3. Yeah. So let me go with A and M. So the I can go with the other this one as well. We have already discussed the same variables within the this one, right? Explanation part. So let me consider A and M itself. Step one. So let's store the original modulus first. So let me go with M0 equals M initially. Let me assign this one initialize M0 to M. Let's move on with the next step. Let's initialize the variables for x and y coefficients here. So I'll just go with x0, comma x1. Let me assign this one to the 0 and 1 respectively, 0 and 1 respectively. Now let's move on with the third step here. Let's continue until a becomes 1. Meaning let me go with the while loop here. While a greater than 1, then q is the quotient, right? So I'll just go with q equals a by m, a divided by m. So this is fine. The next step would be we have to update a and m as per the Euclidean algorithm, right? So I'll just go with a m, m, let me assign the m to m, actually not m minus m equals m, and finally a modulo m. So this is fine, I believe. Yep. The next step here is to update the x0 and x1 that we have considered for the coefficients, right? So I'll just go with x0, comma x1 equals x1 minus this one. We have to consider q into x0, I believe. Yeah, let's go with q into x0. Let's see. The final one is we have to consider x0. This is fine, man. Yep. The next part would be we have updated the q0 and sorry, x0 and x1 for the coefficient. So this is fine. Let's move on with the final step. Nothing but we have to ensure s1 is positive, right? X1, sorry, not s1, x1. So now let's do one thing. I'll write the simple if condition here. If x1 is less than 0, if x1 is less than 0, then what shall we do? I'll just go with x1 equals x1 plus m0, right? So this is fine. Now let's return something. I'll just return x1 here, right? So this is fine. Yep, we are done with this one function to find the modular inverse using the extended Euclidean algorithm. So that's what we have made use of here. Now let's write the function to apply Chinese remainder theorem accordingly with the explanation, accordingly with what we had discussed within the explanation part, right? So I'll just go with def Chinese remainder here. Chinese remainder. Let me go with nums, comma. I'll just go with the remainders, right? So this is fine. So within the Chinese remainder theorem, so let me go with the first step. First step here to compute, first step here is to compute the product of all moduli, if you remember, right? 1 second. Let me initialize prod to 1. Yep. So let me consider simple for loop here for individual n in the nums. Let me go with prod equals prod into n. Yep. So this part is fine. Next, let's go with the result part, man. Let's initialize the result to 0. I'll just go with result. So this is fine. And now let's move on with the step 3. Third step, nothing but here. Let's loop through each congruence equation here. So for I, mm, I. So this is also fine. In zip nums comma reminder. So this is also fine. Uh, yep. We have considered REMS, I believe, right? Yep. Yep. So now within the for loop, MI is nothing but the total product by current modulus, right? So I'll just go with P equals here prod by we consider N underscore I believe. Yeah, this one. Yep. So this is fine. The next step, let's add to the result, meaning what we need to add basically remainder into partial product into the modular inverse, right? A1 into M1 into what we went with Y1, A2 into M1, A2 into M2 into Y2, A3 into M2 into Y2. So that part we have to add to the result, nothing but remainder into partial product into the modular inverse, right? So I'll just go with here result, result equals result into sorry, result equals result plus actually AI this one, yep, into so I'll just go with a mod inverse. So this is fine. Mod inverse of what we need to go with p comma ni. So this one p comma ni. So this is fine. What I need to do here, we have to multiply this one whole by p, right? Yep. So this is correct. Yep. So this is fine, man. Now let's do one thing. We are left with only one step. Nothing but here we have to return the result modulo total product, nothing but this one for the unique solution, right? So I'll just go with return result into prod actually. Yeah, this is fine, man. Now let's do one thing. Let's go with this one example input. So we are done with the algorithm one. So this is it for the algorithm. So two functions. One is Chinese remainder, and another one is this one. What do we call mod inverse? Nothing but the modular inverse. We have made use of the extended Euclidean algorithm, right? Here. Yep. So this is fine. And now let's go with the example usage. So I'll just go with nums equals 3, 4, 5 here. This is fine. REMS. Thus, I'll just go with a 2, 3, 1. So this is also fine. Now let's do one thing. Let's go with a step 5, nothing but let's call the Chinese remainder theorem, right? Function, sorry. So I'll just go with x equals Chinese remainder. Yeah, this is fine. Of let me pass nums, rems. Yep. So this is also fine. Nums 5, this is not taking actually. Nums, let me give m here. Sorry, not nuns actually, it's nums. Yep, so this is fine. The final step here would be, let's print the final answer. I'll just go with the print. The solution is, the solution x is basically, yep, so this is correct. So let me pass the x here. Yep, so this is it for the example usage, right? So now, we have discussed the algorithm step by step. We have the complete idea of the algorithm. Now let's do one thing. What's the output that we need to get here as? This one, sorry. Let's discuss the output part. What is the output that we need to get here, basically? So the solution of x here, we have to get the output 11. So just give me a second here. I'm just going with a one print statement. The solution x is actually, we have to get output 11. The solution x is 11. Why? Because see, so the given congruences here, so 2 3 1, right? So 2 3 1 basically, right? So the given congruences, we can just write it in this way: x 2, this one mod 3 actually, right? 2 mod 3. So this one x equals, next we have 3, this part 2 3 1, right? 3, this one actually mod 4, and this one x equals, this one 1 mod, this one, what do we call, 1 mod 6, right? Or 5, this one numbers we have considered 3 4 and 5, right? So I'll just go with a 1 mod 5 here, right? So this is fine. The total product is nothing but, we will be going with a 3 into 4 into 5. This one, 3 into 4 into 5. 3 into 4 into 5, we get 60 actually, right? The capital M is 60 here. Capital M is 60. This we know. Yep. So for each modulus, so M1 is 20, M1 is 20 here, right? M1 is 20, M2 is 15, and M3 is 12 here, right? So this one, basically, so I can just write it in this way. M1, this one, M1 is 20, just have to apply the formula. M2, we get this one 15, and M3, we get this one 12 actually. So along with this one, let me write the Y as well here. Let me change this one to Y. So this one actually Y1 becomes 2, right? And y2 becomes 3, and y3 becomes 3 as well. Y1 2 because we are going with 20 into 2, nothing but 1 mod 3, right? Y2 3 because we are going with 15 into 3, this one, nothing but 1 mod 4, right? So y3 3 because we are going with 12 into 3, nothing but 1 mod 5, right? So M1 20, M2 15, M3 12, and Y1, Y2, Y3 are 2, 3, and 3 respectively, right? So now let's apply the formula. So somewhere we have written the formula, right? So just give me a second here. This one, if you remember, mm, 1 second. If you remember this one, x equals a1 into m1 into y1 plus a2 into m2 into y2 plus a3 into this one m3 into y3. This one, last we have to go with the mod m, right? Again, x equals a1 into m1, capital M1 into y1 plus a2 into m2 into y2 plus a3 into m3 into y3 mod m, right? So that's what. So now this will be actually x equals, a1 into m1 into y1 is nothing but 2 into 20 into 2. right? So let me write this one 2 into 20 into 2 plus here next one we have to go with a2 into m2 into y2 again. So this one will be 3 into 15 into 3, right? 3 into 15 into 3. Yeah, 3 into 15 into 3. Then the final one is a3 into m3 into y3, right? M3 and y3 you can just look at here 12 into 3. A3 here we have got basically uh, this one actually. A3 here we have 1, right? So this one will be 1 into 12 into 3. 1 into 12 into 3. Yep. So overall you can just calculate here. So this will be first one will be 80. 20 into 2 or 40, 40 into 2 80. 80 plus the second one will be 135 actually. 3 into 15 45, 45 into 3, right? So this one will be 135 and the final one is 12 into 3 36, right? 36 into 1 is 36 itself. So this will be 36, right? So this one we have to go with a mod m, right? Mod m we have got 60 here, so we have to go with mod 60. So this one 80 plus 135 plus 36 mod 60, right? So this one will be if you count, so this one will be 251 mod 60. 251 mod 60, and just go with this one. What do we call 251 mod 60? You can just calculate this one. You'll get the value 11 actually. You'll get the value 11. So 11 is the smallest number that satisfies all the congruences here. 11 is the smallest number that satisfies all the congruences here, right? So 11 will be the solution basically. The output that we need to get here is 11 actually. Yep. So now we have the idea how we got the 11, right? So I showed you step by step, man, by taking the example. Now I hope this one is clear how we got 11 actually. Yep. So if I run the code accordingly with the example that we have considered, we have to get the output 11. Let's check the same. So I'll just go with Control J, Python. Let me go with file name.py. Yep. We have error here. Line number 40. What is line number 40? What we are doing here? While a greater than 1. So this one within the this one, right? Extended Euclidean algorithm for the modern this one. Q equals a by m. So why a here? So let me remove this one. Q equals a by m. So this is fine. Yep. We were getting the this one. So this was the problem, I think. Instead, by mistake, I had typed a along with the q actually. So this is fine. Now, if I run this, yeah, the solution of x is 15060. So this is wrong one. We have to get the output 11. Let's check. Wait, just give me a second here. So here somewhere in the calculation part I have done wrong, I think. So this one has to be modulo actually, not the multiplication operator. So this one is modulo. Let me run this one now. At least I have to get the correct output. Let's check the same. Yeah, the solution x is 11, right? So this was the problem actually. We have to give modulus here. Modulus of the sum that we were considering, right? So we have to go with a modulo actually rather than the this one. What do we call multiplication operator? So that was wrong actually. Result into product. Yep. Now we are getting the desired output, right? So this is it for the this one. What do we call algorithm? Yep. So we have discussed this one step by step along with the output part as well, right? So now, as we have the complete idea of the algorithm, let's do one thing. Let me summarize whatever we have learned so far, right? So let me summarize whatever we have learned so far. Right. So there are some points that we need to this one that we need to discuss. Actually, it's very important. The first point here is concept. Basically, what is the concept of CRT? Nothing but the Chinese remainder theorem here. Chinese remainder theorem finds a unique number that satisfies multiple modular equations when moduli are co-prime. Again, Chinese remainder theorem finds a unique number that satisfies multiple modular equations when moduli are co-prime. When moduli are co-prime. So this is very important. Yeah. So this is fine. Next part. So let's go with the all. Let's this one. What do we call? Let's discuss the algorithm steps. So algorithm steps, first we'll compute the product of all moduli. Right. So first we will compute the product of all moduli, right? So that's what we do. The second step here, for each modulus, compute the modular inverse of partial product. Modular inverse of the partial product, right? So the third step was, if you remember, we have to combine the results using weighted sums and take modulo total product, right? So we will be combining the results using weighted sum and take the modulo total product and take modulo total product, right? So this is fine, I believe. So these are the algorithm steps actually. Next, let's discuss the time complexity. So what's the time complexity of the algorithm that we have written here? This one, time complexity of the Chinese, this one, remainder theorem. So that overall time complexity would lead to big O of n log m, right? Big O of n log m, right? So due to modular inverse computation, we are also computing the modular inverse, right? Using the extended Euclidean algorithm, the first function, if you remember, yeah. So overall time complexity would lead to big O of n logarithmic m. Yep. So what would be the space complexity here? Space complexity would lead to big O of 1, right? So the time complexity and the space complexity for the code that we have written as big O of n log m in the big of 1 respectively, right? So these are some of the points I wanted to discuss with you guys. So these points you have to keep in mind when it comes to Chinese remainder theorem algorithm. Yep. So we are done with this particular algorithm. Next we will be discussing about the Euler's totient function algorithm. Usually we call this one as Euler's totient function. Yeah, we'll be discussing about the Euler totient function algorithm. Yeah, for now this is it. Thanks for watching, guys.